Okay. A linear equation, whether it is the equation for a line or a plane, depends on the number of variables involved. But I want to look at more general ideas for a bit. And the theory of surfaces in 3 dimensions can be a lot of different things. Oops, wrong button. That one. But let's start with some simple ideas. Well, simpler ideas. If I create a surface in 3D, it is possible that that surface does not touch any coordinate planes. The homework question asked you to find me the largest sphere with a given center that would fit in the first octant, right? And you said, oh, well, as soon as I touch one of the coordinate planes, I've gone too far. If I cut the radius of that in half, then that would not touch any of the coordinate planes. But it is often that exact surface connection, that intersection, that we want to draw to give ourselves a good picture of what that surface looks like. So frequently we will draw the intersections of a surface with one or more of the coordinate planes. We'll call such an intersection curve a trace or a cross section. And sometimes we won't just use the coordinate planes, we'll use planes parallel to the coordinate planes. Okay. So instead of just saying, I'm going to look at where my surface crosses the XY plane, I can say not only am I going to look where it crosses the XY plane, I'm going to look where it crosses a plane of height 2, or a plane of height 4, or a plane of height -2. Or maybe I'll say I want to look at where it crosses the XZ plane, as well as y equals -2, or y equals 2, or y equals 4. So I can build this view of what my surface looks like by slicing it into different pieces in different directions. 99.99% of the time, those slices are made parallel to one of the coordinate planes. Questions? So far, so good? What shape does that equation describe? If I was only in 2 dimensions, absolutely, it would be a circle. But I'm starting to think in 3D now. So my problem is that there's no z in that equation, right? It should be a circle. But because there's no z there, I can think of z as a free variable, a parameter, as if it doesn't matter, which means I should have that circle no matter what z I pick. Yes? That sounds like my cross-section idea. When z is 0, I have the circle in the xy plane. So if I specify that z is 0, I can draw this in 3D. As a circle in the xy plane of radius 1 centered at the origin. Now, here's where I have to use what little artistic talent I have, because I want to show that this is in the xy plane, so I show it going over that, but under this. See how that little gap kind of indicates that the top of the z-axis is in front of it from my perspective? But that's the circle at height 0. What about at height 3? Does that equation change if I tell you that z is 3? Does that equation change if I tell you that z is -2? Z in that equation is irrelevant, yes? So let's take this circle and draw it parallel, above, or below, at any other height you want. You should see a cross section that looks exactly like this circle, yes? So that means up here, there's another circle directly above that one, at whatever height we want. There's another one below, yes? What shape have I made? Aha. And it extends infinitely upward and downward because z is a free variable. And if you think about it, those dotted lines that I've drawn, if you take a sheet of notebook paper and roll it up, there's my circle, x squared plus y squared equals 1. And the lines on my notebook paper just became those vertical lines that we've drawn here. We call these the rulings of our cylinders, like we took a ruler and drew along the free axis, our free variable. I hope the image is not too psychotically badly drawn and that you see what's going on here. What's interesting to me is that there's absolutely no requirement that the curve I start with is a circle. That's not a circle. The hell is that? Parabola. I could write it on the other side, right? Y equals x squared. Okay, that's the parabola y equals x squared. But in 3D, that's got no z's in it. So I would say exactly the same thing that I said about that circle, about this parabola. Oh, in 3D, I should get the parabola y equals x squared in the xy plane. Now, this is going to look horrible. But in the xy plane, I have a parabola. Now, really, That's drawn on the floor. And as we go, as I start in the corner over there as the origin, as I come out the wall towards you, the parabola comes out into the middle of the room. It also goes back into the room behind me. That's this part of the parabola in the room behind me. This is the part that's in our room. Assuming I put the origin in that corner. But again, I can think of taking that and moving it to any height I want, yes? So what I have is a cylinder over a parabola. The traditional cylinder is a cylinder over a circle. We've lifted that circle up and down, but now I'm saying take this parabola and lift it up and down, and we can create that same set of rulings. So up here, somewhere, I should have a parabola again. And down here, again, I'm a lousy artist, but these should be connected up and down. I'm going to call this cylinder idea. Generally, if I have any curve, I can create a cylinder by extending that curve in the direction of the variable that's missing. I'm going to tweak this a very small bit. Ready? How does that change the picture we just drew? Yeah, because my original parabola now should go this way. Out into the room in front of us and back up behind us. And that means that the rulings go left to right. It's sideways. So I have a piece of paper, but instead of making a cylinder that is standing on its side, I've made a trough. There we go. And if I did y equals x squared, we're going forward. Because the x would be, I'm sorry, z equals y squared. Here, let's get really wet. What's that one? My first reaction, I'm missing a variable. This is a cylinder. I just need to know what the base curve looks like. So I know it's a cylinder over what? So I'm going to think of this in 2D. Only the two dimensions are the y and the z. What is this equation in y and z? Almost. It's not quite a circle. It would be a sphere if it had all three variables in it. right? Because sphere is x squared plus y squared plus z squared equals r squared. That only has two squares. An ellipse, an oval. If I remember, oval ellipses always had ones on the other side. So I'm going to divide everything by 36. That's an ellipse. I remember that. The standard form of a conic section, chapter 10, section 5. We did do this crap. Oh, man. So now I can draw that ellipse in y and z. And I say to myself, oh, well, if z is 0, then y is plus or minus 2. And if y is 0, then z is plus or minus 3. So I have a major axis and a minor axis, and I have this oval here. If I really want to, I draw the box and I make it all look right. But now I'm in 3D, so what happens? Let me add the x-axis. What should I see in 3D? The cylinder should be coming out at us along the x-axis with cross sections that look like this ellipse. Now, sometimes we'll actually say it's over an ellipse and it's along the direction of the rulings. So this particular ellipse lives along the x-axis over an ellipse. Sorry, this particular cylinder lives over an ellipse along the x-axis. That would mean that this one up here, this parabolic one, was along the y-axis. And this one was along the z-axis, because that's the direction the rulings went. You'll also hear this, you'll see textbooks that shorten this. This is an elliptic cylinder. Okay, I'll buy that. But in this particular this particular graph, all I've drawn is the cross section, the trace on the YZ plane. I should indicate somehow that there are rulings but I also happen to have a computer, right? On my computer, built into the MacBook, is a graph. If you don't have it pinned to your taskbar, you can go to the launcher and launch it under Other. There it is. In mine, it's the top center. I'm going to launch that, and then I'll share it with you all. So here's my grapher. And notice, share screen, share grapher. Notice it gives me the option of graphing in 2D or 3D. I'm going to go to 3D, and I'm going to start with this default white system. And you can see it slowly turning there in 3D. We have a right-handed system. I see X and Y with the little arrowheads on them, and Z sticking up. So let's use that. And now, no, I don't want you to pause my screen share. I want you to use that screen share. Let me reshare that. There we go. Share. There. Now you can see the thing I'm sharing. Good. Notice up here, it writes my equation, Z equals. I'm going to change that. Let's do the one we were just looking at. 9y squared, come out of the exponent, plus 4z squared, come out of the exponent, equals 36. And the computer knows what's x, what's y, what's z. It'll draw that. And you can clearly see the rulings along this cylinder. You know my favorite part about this picture? you can grab it and move it to whatever perspective you want to see it from. You can set it in motion and it'll start turning in different directions. There, I can see the ruling's a little more clearer, can't I? You can even adjust by right-clicking on this, edit appearance. You can adjust what things you see. And notice you can put a uniform color or stripes. Or a checkerboard, or all sorts of behaviors on this. You can put contours on it. Contours. Those are our rulings, aren't they? They're even in a contrasting color right at the moment. But notice those are also cuts parallel to the XY plane, aren't they? And they're in different colors as we go up. All sorts of options are available to us using that edit appearance behavior. They've knocked out the close on that. Why is there no close? Edit. Where's close inspector? You took it away. I'll click over here. It'll go away. Yes. Okay, fix that. There. There's my surface. You want one of the other ones? Sure. I can do it as a new one on top of this one. Equation, new equation. Here, we'll make a new equation. Z equals X squared. That was our parabola, it's a parabolic cylinder. There it is with the checkerboard this time. And it's going along the y-axis instead of the x. Now, if I really wanted to, again, edit appearance, I can change the color. I don't want the color. Let's make it something else. Uniform color. And now it'll just be one color. Poof. Select that color. There we go. You can even make it kind of transparent, so you can see both of them at the same time. Draw all this stuff. I know drawing it by hand is what I like to do. It's what I was taught to do. I like being able to make these drawings, but I'm so much happier that I can do this here because I am a crap artist, people. This is just much easier. And when it comes to drawing stuff, I don't want you to draw stuff by hand. I want you to be able to recognize what something is. Tell me what it is. Tell me intercepts if we're going to have them. Like I did with the elliptic cylinder, I was able to say that, oh, the top and the bottom were at a height of 3 on the z-axis, the left and the right were at a height of 2 on the y-axis. So I can do all of that. I don't have to do it manually. Questions? Cylinders are missing a variable. Planes were not missing a variable. Spheres were not missing a variable, right? So when we were looking at spheres, we had an equation that looked like that. But everything in there is squared. I mean, if I were to multiply it out, I'd get, I don't know, the 2xh part and the 2yk part, right? I'd get all those other pieces from doing the squaring, yes? Again, in the homework, you had to go backwards. You started with an equation, then you found the center and the radius, right? So we've done the reverse, but what about in general? Because this is a degree 2 equation, and it describes a surface in 3D, we're going to call a quadric surface any surface that is defined by quadratic equations in variables. Now, the problem is that means I can have lots of quadratic combinations. So I could have something with an x squared, and something with a y squared, and something with a z squared. But wait, there's more. I could have something with an xy, and something else with an xz, and something else with a yz. Those are all technically still quadratic. And I could have then just the numbers x and y and z, and maybe a number all alone. Then that whole thing equals 0. If I move the r squared to the other side, I would get a 0 over here on the right. So that's a general quadric surface. And it's got a whole lot of crap going on in here. And I hate this equation. So I'm going to do some rearranging. Let me do some moving. What's the easier version of the equation of a sphere? If I put the center at 0, 0, 0, I get rid of h and k and l, don't I? I can do the same thing here. And if I put the center at 0, 0, 0, then I can get rid of all of these pieces, or at least two of them. If I rotate this so that it's either parallel to the x-axis, parallel to the y-axis, parallel to the z-axis, I can get rid of all of these. So it turns out that by rearranging, with some work, there's a lot of algebra involved here. It's some of the rotation matrices that we did at the end of linear, where we're diagonalizing our quadratic form. Remember that crap? And you're like, what the hell am I going to use this for? This is what I'm using it right here. I'm making all of our equations that much simpler by turning things so they line up with the coordinate planes and moving the center to 0, 0, 0. It's a standard form trick. Now, that top version, it's going to have one variable. It could be x, it could be y, it could be z. If I try and align things so we're always centered around the z-axis, I'll usually end up with a z there. But I can take that entire picture and turn it to along the x, and I end up with an x there. If I take that picture and turn it to along the y, I end up with a y there. Or I end up with a number. So I end up with just the squares, and then either one linear thing or one number. You got a question? No? Okay, I was hallucinating. It's okay. I'm allowed to miss things. But it turns out that all of these equations are 3D versions of conic sections. Which means if I can identify what's going on, I don't have to do anywhere near as much work. So this is another case where the form of the equation is what matters. Like we were able to tell, oh, that's a parabola. Oh, that's an ellipse. I remember there were hyperbolas as well, right? So if I have those conic section images in my head, I should be able to figure out what they look like when I do 3D things to them. I'm not going to make you memorize this. When the exam rolls around, you get a 3x5 card that you can write anything on it that's not an example. Definitions, theorems, tables. You can't actually put numbers in it, but you could take the table that is on page 837 that shows you what all of these look like based on the equations. All right, wait a second. I need to zoom in on this. I need to understand what the hell is going on here. Okay, wait a minute. Number x squared, number y squared, number z squared equals 1. That's this version of the equation. Only what I did is I moved the number to the other side and then I divided to make it a 1, just like we did with our ellipse, right? And what do I get? I get an ellipse. I get an ellipse in 3D. It's an ellipse in the XY plane. It's an ellipse in the XZ plane, and it's an ellipse in the YZ plane. And if some of those bottom numbers are equal, then instead of having an ellipse in that direction, we have a circle in that direction. If all of them are equal, then we get a sphere. Okay, wait a minute. Wait a minute. Wait a minute. I'll come back to this table. That looks like this. That's our second version of the equation. X squared over 2 plus y squared plus z squared minus 1 equals 0. First thing I'm going to do is put that 1 on the other side. With me so far? Now, artwork is a disaster for me. So instead of drawing a 3D picture right away, I'm going to draw some 2D pictures. What happens if z is 0?
Yes, the XY plane.
So I have a cross section, right? Like I cut it right at z equals 0, and the resulting shape is an ellipse. That's the XY trace. We cut it at z equals 0. And when I do that, y up here, x down here, I have x squared over 2 plus y squared equals 1, and that's an ellipse. And I know that that particular ellipse is longer in the x direction than it is in the y direction, because that's x squared over 2, it's y squared over 1, right? And now I do the same thing we did when we were drawing the ellipse earlier. And I say, okay, that means if y is 0, x is going to be plus or minus the square root of 2. So I'll need to go out to the square root of 2 on each side. And if x is 0, then y is plus or minus 1. And I have an ellipse. So I know right away that in the x direction and the y direction, looking down from above, I should see a picture that looks like this. But I really should see a picture that if I look at this with my head tilted sideways, because X goes in front of it. So the long direction should be the front, and the short direction should be the left and right. So it should look like that from above. Nora, you're squinching at this. Talk to me.
No.
Okay. Well, that's this cut. What if I cut it a different direction? Do you want to do X and Z or Y and Z first?
One.
Okay, if I do Y and Z, so the YZ trace would have X equal to 0. Again, I go back up to this equation. What's the equation look like when X is 0? Oh, just go up here and eliminate X, and you get Y squared plus Z squared equals 1. What's that? Right, it's an ellipse where the two distances are equal, so it's a circle. It's the unit circle. I recognize that one. Now, if I were physically building this object, this shape that I want to get, I could take a circle made out of wire and put it this way. And I could take an oval made out of wire and put it this way. And that would be the start. But then I could also say, I want to know what's going on this way in the XZ direction to build ribs that go around. So let's do one more trace. We do XZ. And that means that Y is 0. And then I get a third picture. But when I crop out Y from my equation, that equation looks really familiar, doesn't it? Isn't that the same equation we had up here? Only changing X for Z for Y. So that means that this trace is also an ellipse. And it's an ellipse the same size as the ellipse we had in X and Y. Now, here is where we reach the limit of my artistic ability. I want you to take all three of those curves, and I want you to draw them in 3D. Now, at the moment, I'm going to do this by hand, but you should also do this on the grapher. If you've got your computer with you, if not, do it later in the grapher. But the first thing I'm going to do is I'm going to label the intercepts, because I know I cross the x-axis here at positive square root of 2 and back here at negative square root of 2. I cross the y-axis at 1 and negative 1. I cross the z-axis at 1 and negative 1. Ready? I'm going to draw the YZ trace first, because the YZ trace is a circle and the YZ plane is the piece of paper. So I can say that the YZ trace is this circle. Now, what's the XY trace? The XY trace was the ellipse, but it's long to the front and back. So it goes from this point here, and then around the back, and then back up on the side, and back to the front. So that's sitting this way. That really looks horrible, doesn't it? But now I need to do the same thing vertically. In the X and Z plane, I need to go from up here down to the front. And I need to go from up here out to the back. And then I need to go underneath and up the front. What I've got looks like more like a rugby ball than a football because it's not quite pointed enough for a football. But that looks like a football with rounded ends. A really weird looking blimp. But there's my ellipsoid. And what's more, this particular ellipsoid has a circular YZ cross section. If you cut this in the YZ plane, you got a circle. As you move forward, you get a circle. As you move back, you get a circle. So we see circles that get smaller as we move front to back. We see ellipses as we go from top to bottom or from left to right. I am a horrible artist. That's why this sucks. But there's a big head space jump from seeing this as a flat object to seeing it in 3D. And seriously, if you got a little toy football somewhere, look at it from all those different sides and see if you can see where the cuts and the cross sections would be. Play-Doh helps a lot here. Make the shape out of Play-Doh and then slice it with a knife. See what it looks like when you cut it across. Now, that's this one. And it's based on the idea that this equation here, this looks like an ellipse. I mean, that is the equation for ellipse if I get rid of the z, right? That's the exact equation we were using for an ellipse on that chapter 10 handout we got from last semester. But what if instead of having a number here, I didn't have any number at all? Remember, we said we could either have a number or we could have one linear piece. Well, this doesn't have any linear pieces. Z squared equals X squared plus Y squared. If I got rid of one of those, that would be like number, I'd take the square root, right, to get Z equals in terms of X. And if I did that, I'd get a line. Actually, I'd get a plus line and a minus line because I took a square root. I got two lines. Now do the same thing in X and Z and Y as you did in Z and X. I've got a cone. If I slice it, I get an X if I slice from top to bottom. But going this way, I get ellipses, depending on the size of these numbers, A's, B's, and C's. Because here, if I fix a Z value, then I get an ellipse equal to 1, or whatever number this is, right? I can do that. This is a straight line that's been twisted around a point. This is an ellipse that's been rotated in 3D. We did, remember that in Calc 1? We did volumes of revolution. Holy crap, that ellipsoid is a volume of revolution. I took the ellipse and I spun it around. This shape. If I cut that either front to back or side to side, parallel to the z-axis, I have a parabola. Might be different size parabolas. This could be skinny in one direction and wide in another direction. And that's what makes the cross-section parallel to X and Y an ellipse. If those numbers A and B are the same, then we'll get a circular paraboloid rather than an elliptical paraboloid. Notice, though, that the z is to the first power as opposed to in the cone where it was to the second power. That's why I didn't take a square root this time. Okay, I have an ellipse rotated gave me an ellipsoid. A line rotated gave me a cone. An ellipse A parabola spun gives me a paraboloid. What's left? A hyperbola. But now I have to make a choice. Which way are you going to spin the hyperbola? Are you going to spin it around the x-axis or around the z-axis? If you spin it around the z-axis, you get a tower. There's the hyperbola on the edge, right? But you spun it around this way. That is exactly the shape of a power plant cooling tower. You know why? Because you can build it out of straight lines at an angle, rotating around. So if we rule this in a different way, all the rulings are perfectly straight. But I can see my hyperbola and I can see the rotation. On the other hand, if I rotated it this way, I'd have two separate pieces with a gap in the middle, right? So one sheet because it's one piece, two sheets because it's two pieces. But there's my hyperbola again. Sneaky son. How dare you? Drawing the traces are not easy here because some of the traces will not exist. There's a gap in the middle here. Why? Oh, because there'll be some negatives floating around and you can't take the square root of a negative. Notice only one of these numbers is positive. The other two are negative. Up here, two are positive and one is negative. So the way our signs pair up allows me to tell which kind of parabola I have. I like that. The last shape is the one that pisses the most people off. This is called a hyperbolic paraboloid. What the? There are actually two different sets of hyperbolas here. On the top, in this picture, we've got a hyperbola going in x and y. I'm sorry, in the y direction. Because I can see that we extend out here in the y-axis, right? Up here, we have a parabola going this way. And this way, a hyperbola going this way and this way. Down here, though, at the bottom, our hyperbolas go in the x direction. So it kind of shifts in the middle there, right? But it turns out that if you cut this parallel to the xz plane, you see parabolas. Look at these lines right here. These are parabolas. But if you cut this way, you get parabolas that go down. So you have parabolas up in one direction and parabolas down in another. Take your hands, make your parabolas. Now, with your thumb on one hand, put your joint between your thumb and your forefinger at the top of your thumb on the other hand. Now, as you move this across, see how it sweeps out that weird shape? Now, do it the other way. Move this one front to back. You have this on your hand. If you point your forefinger out and your thumb up, your palm to back of your hand goes down, and your thumb to forefinger goes up. You've got the two parabolas right here with you. I never call this a hyperbolic paraboloid. You know what I call this? A saddle. Because damn it, that's what it looks like. In this case, I would be facing side. But I have these with me all the time. And this is the one which is a hyperbola on one side and then a linear equation on the other. So if I only had one pair of variables, hey, that's a set of parabolas going up. That's a set of parabolas going down. This is why I don't want you to memorize this crap. You should put a bookmark on page 837 and use this. If instead of using a square cutout of that saddle shape, I made a round cutout of this saddle shape, this would be a Pringles potato chip. Math you can eat. Should have burritos and Pringles for lunch, right? Cylinders and hyperbolic parabolas. All of this is predicated on the idea that what we really did was just move our quadratic equations, our conic sections up. What happens in 3D when I take these equations and generalize? Okay. On Monday, I want to go back to our vector descriptions, because when we start looking at two or more of these at the same time, we see that they intersect in weird ways. You saw that when I drew the cylinder over the parabola in red and the cylinder over the ellipse in green, we had that funny place where the two of them intersected. But that's a curve in 3 dimensions. I know what a line looks like in 3D. We did that yesterday. What's a curve look like in 3 dimensions? That's Monday. So I will see you all then. Hope you have a wonderful week.